Welcome to the second lecture of formal models. Today we will continue with our recapitulation of finite automata, which serve as an important concept for many other modeling languages which we will introduce during this course. So the last time we formally introduced the finite automata concept and we saw how we will define it within this lecture. Finite automata are a very popular modeling language, and there are different ways how they can be defined, but overall they are equivalent and contain the same kind of information usually. Yeah, but the notation might be different and also a bit how they look like. So then we have seen properties like determinism and completeness, and we wondered how we can get a non-deterministic or non-complete automata into a deterministic and complete one that accepts the same language as the original one. For this, we introduced the concept of power automaton, which has the drawback that there might be an exponential blow-up in the number of states. As a workaround, we introduced the oracle automaton that use a very simple trick to formally get rid of non-determinism, and the trick is to encode non-deterministic choices into the labels of the transitions. Yeah, and by this we get formally deterministic automata and can, for example, use them with tools that expect such kind of automata. And today we will continue with product automata, and this allows us to get the intersection of the two languages described by two automata, and so we can find common words in a language, and we will also see what we can do with this construction in order to perform verification tasks. In particular, we are doing one kind of model checking. Then we will conclude this lecture and this topic with transducers, which you maybe also have seen in a digital design course, where we have finite automata that not only describe or cannot only be used for the acceptance of a word, but which can also produce words as an output. Yeah, so this is the plan for today. In order to solve certain verification tasks, I would like to introduce the product automaton as a next concept. And the product automaton allows us to relate or compare the languages of two automata. In particular, the product automaton gives us the intersection of the two languages described by two automata. So we can identify the common words of the languages of two automata when we do the product automaton construction. And yeah, let's have a quick look how the product automaton is defined, and then in two examples I will show you how to practically construct them. So we are given now two automata, and they have different states, different initial states, different transition relations, and different final state, but they have the same alphabet, otherwise it would not make much sense to calculate the joint words. Yeah, so we have given these two automata, and then we define the product automaton as follows. The states of the product automaton are simply a pair where the first component is a state of the first automaton and the second component is a state of the second automaton. Then the initial state are also the cross product of the initial states of the two automata. Same with the final states. So we have a pair of two final states. And now how is the transition relation defined? So if we have a state that consists of component S1 and S2, and we have a symbol A, then this has a target state S prime 1, S prime 2, if and only if it is possible to go from S1 with an A to S prime 1 in the first automaton, and if it is possible to go from state S2 with an A to state S prime in the second automaton. Okay, and this construction gives us an automaton for which it is easy to show that the language of the product automaton is the intersection of the language of the first automaton with the language of the second automaton. So we have a description of the set of words that are accepted by both A1 and by A2. And if the intersection is empty, then also the language of the product automaton is empty. Okay, so let's look at two examples, one which illustrates that there is an intersection and one which illustrates that the intersection is empty. In the first example we are considering, there are two automata given which looks as follows. So the first automaton accepts those strings that start with AB and then have something afterwards, can be empty, can be an arbitrary sequence of A and B. And the second automaton describes those words which end with BA. Yeah, and in the beginning we can have an arbitrary number of A's and B's. So the joint alphabet, sigma, is AB. And now let's see how we construct the product automaton. If I would do it on Blackboard, I would show you that I will use my fingers and point to the state I'm currently handling. So I now mark it with red. I'm now handling this state and this state. So we first start with the state S0, T0. And I do not write the pair notation, but I just write the two states. Yeah? So we begin with S0, 20. We have only one initial state in each of the automata. Therefore, we have also only one initial state in the product. Okay, the next thing is we have to check where can we go with A and where can we go with B. With an A, we can go to S1 here, and with an A, we can go to T0 here. So in the product automaton, we go with an A to S1 T0. Then we have the problem that in automaton A we cannot do a transition with a B, therefore S0 T0 doesn't have any transition. So the next state we are handling is now S1 T0, so we are here. And now we have to check where can we go with an A, and with an A it's not possible to proceed in automaton A, so we cannot do an A step, but we can do a B step, and with a B step we go to S2, and there are now two choices. We can go to S2 T0 with a B, or we can go to S2 T1. Yeah, since here we have two options for the B, this is also reflected in the product automaton. Okay, so which state do we handle next? Let's handle next S2 T0. Okay, what can we do here? If we have an A or a B, we can stay here, because we can, with AB we stay in S2, and with AB we stay in T0, so we have AB here. But we can also do a B, and this extra B brings us to state S2 T1. But now we are done with the state S2 T0. Okay, what is the next state we're handling? And I overlooked that this S2 D1 I have already here, so I quickly erase it. And I can draw the B edge to the state here. Okay, so let's proceed with S2 T1 here. And what can we do here? We can proceed with an A, and the A brings us to S2 T2. Okay, and nothing else we can do, because in B there is, in automaton B there is nothing we can do with a B. Okay, so finally we have to consider this S2 T2 state here, and there is nothing we can do because the T2 in automaton B doesn't have any outgoing edges. Only one thing is missing. We have to identify the final states, and in A and B we have one final state each, S2 and T2, and hence the only final state in the product automaton is S2 T2. Okay, and when we now look at what kind of words are accepted, then obviously the shortest word is A, B, A. Yeah, so it starts with AB and ends with BA. And yeah, we have, because of this path here, so because of this path from S0 T0 to S2 T2 we have AB, and also if we go to S2 T1 we have AB, and in all paths to the final state we have a BA as well. So indeed we have a combination of so we have indeed the intersections. We have those words which start with AB and end with BA, now covered by the product automaton. Okay, this was the first example I will show you. For the second example, we consider the automaton which describe the words starting with AP again. And as a second automaton, we now consider another one. This automaton accepts the empty word, and it accepts the word consisting just of the letter A. Yeah, so a very simple language that is described by automaton B, but we see we have no word described here that starts with AB. Okay, and what does this mean for the product automaton? Since we have now two initial states in automaton B, we also have two initial states in the product automaton. Oops. So the first initial state we have is S0 T0, and the second initial state we have is S0 T1. Okay, and now let's see how we proceed from S0 T0. Oops. From S0 and T0 we can do an A step, and the A step brings us to S1 T1, and that's it. Now let's consider S0 T1, and obviously there is nothing we can do because T1 doesn't have an outgoing edge. Finally, we consider S1 T1, and also here we cannot proceed because T1 still doesn't have any outgoing edge. Okay, so that's it. And now we have to check if there are final states. And the final states have to contain S2 and T1, because these are the final states of automaton A and B. But we do not have any state S2, T1, and therefore this automaton we have here, this product automaton, has no final states. And therefore the language of this automaton is empty. And so the language of A cross B is empty. And this means that A and B do not have any joint words together. Yeah, this was the second example I wanted to show you. Okay, and now finally let's talk about how these concepts we have seen so far can help us to verify a system. Assume we have an automaton A, which is the program which we are implementing, or the system that we are describing, and we have an automaton S, which is the specification that A should satisfy. Okay, what does it mean? We have S, the language of S. This is a set of words, and A is correct, the program is correct if the language of A is a subset of the language of S. So only words are accepted which conform to the specification. Yeah, this is the scenario what we want to have. And the problematic scenario is, this is okay. The problematic scenario is if we have the language of S and the language of A contains words which are outside. Yeah, then this means we have some kind of problematic behavior here. So A does something what it is not allowed to do. And if we have now the automaton describing A and the automaton describing S, we want to figure out if there are words outside of the specification which are accepted by A. And how can we do this? Yeah, we can do the following. We can say we negate S, so we do the complement of S, and build the cross product with A. Yeah, so if we do the complement of S, yeah, then, and if this is the set of all possible words, and the complement of S are exactly those words which are not accepted by S, and if we build the product and we figure out that the language of this product automaton is empty, then we can conclude A conforms to the specification to S. Yeah, because then there are no words that are outside of the specification of S. Yeah. Let's have a look at a small final example. And I'll start with a new page. Say that S is the automaton which accepts words with one A or with two A's. And so this is a final state, and this is a final state. So the language of S is A and AA. And now say we have a program which, it's a very small example, it's which produces an arbitrary number of A's. Yeah? And here we immediately see that we have a problem here, but with the power with the construction I've seen before, we can easily identify the problems. So here we have an automaton S, which is deterministic, but unfortunately it's not complete, so we cannot do the complement of it directly, so we quickly have to do the power automaton of S in order to make it deterministic and complete. How do we do this? We have S0, and then with an A we go to S1, and then with an A we go to S2, and with another A we go to the empty state where we stay forever. Okay, and final states. Okay, now I made a mistake. Final state is not S0 is not the final state, but S2 and S1 are the final state. So this is the power automaton of S. Now we need the complement of the power automaton of S. And this is simply, now S0 is a final state, then S1 is not a final state, S2 is not a final state, but the empty state becomes a final state. Yeah, so the complement automaton accepts all words except A and AA. Yeah, this looks good. And when now we have that, we can do the product automaton of say PS, and our program, I called it P. Okay. And we have this one is called T0. So we have one initial state, which is S0 T0, and yeah, then I could proceed in constructing it, but already here we see the problem. Yeah. S0, T0 is a final state, because T0 is a final state, S0 is a final state, and therefore in the language of this automaton we have the empty word, and the empty word, hence the empty word is an element of the language of P, but the empty word epsilon is not an element of the language of S, and therefore we already have found a problematic case where we see that the program accepts a word that is not conformant to the specification. Yeah, and with this we can figure out that the program and the specification do not fit. If they would have fitted, then the intersection would be empty and everything would be fine. Yeah, and with this I would like to conclude the lecture of today. So we have discussed the concept of finite automata. We have discussed important properties, particular completeness and determinism. We have seen how we can make an automaton that is not complete and deterministic deterministic and complete by using the power automaton construction. We have also seen Oracle automata and optimized Oracle automata as some trick for making an automaton deterministic by using a dice and encoding the indeterminism into the labels of the transitions. And we concluded with the product automaton, which allows us to build an automaton that describes the intersection of the language of two automata, which is one way of verifying the correctness of an automaton. Okay, thank you very much for watching. Before I proceed with the concept of I/O automata, I would like to show you the following example, which illustrates how a hardware circuit can be represented in terms of a finite automaton. This example gives us also the transition to the I/O automaton, as we will see. But let's have first a look at this picture here on the left. And what we have here is a circuit that contains two logical gates. Here we have an AND, and here we have an XOR, and we have also two D flip-flops. How they internally work does not matter. What is important is that they are having the same clock, and when there is an input at a certain point in time, then at the next time point we have here at the Q this respective output. So for example, if we have here a 0 in at time point t, then at time point t plus 1 we also have a 0 here. This Q prime, what we have here, is simply the negation of Q. And this prime is often used as a symbol for the logical NOT, and it negates the value of the Q. Okay, and with this we can model some, or this circuit has a certain behavior, and this we want to encode in terms of a finite automata. We will for the moment ignore that there is an output, and what is also important here is that we do not have any input signals, but it would in principle be no problem also to encode inputs here. Okay, so I will switch to my writing pad. First of all, we have to figure out what states this circuit can take. And since we have two flip-flops, X and Y, we can represent the states as a 2-bit vector consisting of the components X and Y. Yeah, so the value of this X flip-flop and the value of the Y flip-flop define the state of the circuit. For convenience, I write not always the pairs, but I just write X, Y, and if X is set to false, then I write a 0, and if it's set to true, I write a 1 at the first component, and the same for Y. So for example, 0, 1 denotes that X is set to 0 and Y is set to true. Okay, and since we have here 2 bits that define the states, there are 4 possibilities. We can have state 0, 0, state 0, 1, state 1, 0, and state 1, 1. And the question is now, how are these states connected by the transitions? And for that purpose, we do a truth table. On the left-hand side, we have all possible values of X and Y. So we have 0, 0, 0, 1, 1, 0, and 1, 1. And on the right-hand side, we have the next state variables. So we have X prime and Y prime. And this prime here is a different prime than the prime we have here in the flip-flops. Here in the flip-flop, it was simply the negation of the output of the flip-flop. Here the prime indicates that we are talking about next state variables. And the values of the next state variables are defined on the values of the current state variables. And if we want to know what is X in the next state, then this is an XOR of the value of y and of the value of x. So x prime is defined as x, x or y. So when x and y are different, we have a 1, and when they're the same, we have a 0. So we get 0, 1, 1, 0. We do the same for the y prime. For y prime, we have to look here, and y prime is simply the negation of y, so this is not y. And for the y prime, we therefore simply flip the values of y, and we have 1, 0, 1, 0. Okay, and this gives us the transitions between the states. If we are in state 0, 0, then we go to state 0, 1. If we are in state 0, 1, we go to state 1, 0. If we are in state 1, 0, we go to state 1, 1. And if we are in state 1, 1, we go back to 0, 0. And maybe you see what we have, what kind of circuit we have here. It's simply a modulo 4 counter. This number can be interpreted as 1, this is a 2, this is a 3, and this is a 0. Yeah? So this circuit does increases the value, or we represent by the state variables always by 1, and if we're reaching 4, we do a wraparound and continue with 0, 0. Note that we do not have any labels on the transitions because we do not have any input signal that would give values for the transitions, but in principle there could also be an input line, and then we would use this as labels for the transition. And now the question is, what is about the final states and the initial state? Initial state is not specified here, so we can select any value or any state as initial state. For example, here 0, 0 would maybe make sense. Yeah, for the output, or we will use the output for the final state, and let's calculate what is the value of the output. For this we use again our truth table, and we have to figure out what is the output. The output is simply the value of not x and not y. So we have a 1 in the first line, and then we have 0, 0, 0. And we can say, okay, when the output becomes 1, we are in a final state, and therefore we would mark 0, 0 as the final state, because then in the next cycle we get a 1. Yeah, and this gives us a first example how digital circuits can be represented in terms of finite automata, but what is not so interesting is here, or what is a restriction, is that we can use the output of the circuit only for modeling acceptance or non-acceptance, but sometimes we also want to have the full output as a result. So we want to produce an output word based on the given input word, and this we can do with the I/O automaton, which we will introduce next. An I/O automaton consists of the following components. So first of all, we have a set of states S. This set of states is usually finite, but in principle there is no problem if it's infinite, so there is not really a restriction on that. Then we have exactly one initial state from the set of states. This is important because the I/O automaton should be deterministic, and therefore we have the restriction that there is only one initial state. Then we have the input alphabet sigma, which defines how the words look like, or which symbols the words contain that are read by the I/O automaton. And based on this input alphabet sigma, we define a transition function. It's important here now we have also a function and not a relation, meaning that it's always clear what is the next state when we read a certain symbol, and they're not non-deterministic choices. So the transition function takes a state and a symbol from the alphabet and maps it to the next state. So when we read a symbol from the alphabet and we are in a certain state, then we know what is the successor state. In addition, we also have an output alphabet, so we do not have only an input alphabet sigma, but we also have the output alphabet delta, and this output alphabet is used to produce words as output, and for this purpose we have an output function O, and this output function maps a state and a symbol from the input alphabet to a symbol of the output alphabet. This kind of I/O automata, as we have defined it here, are also known as Mealy machines in the literature. There is an alternative definition which is known as Moore machine, and these Moore machines are defined in a similar way, but the output function is different. When we have a Moore machine, the output function maps only a state to the output alphabet, to a symbol of the output alphabet. So we do not label the transitions with the output symbols, but we have this information directly with the states, and this has some consequences how this kind of automata are used, but it can be shown that in terms of expressiveness, Moore and Mealy machines are equivalent. Now let's have a look how we can represent the circuit we are given here in terms of an I/O automaton. In contrast to the previous circuits, we have now also an input and not only an output, which we have to consider in our I/O automaton model. And the input alphabet is obviously 0 and 1, and the output alphabet theta is also 0 and 1. And we have two flip-flops, A and B, and several logic gates, and these define us how we have the state transitions. Now let's have a look how we get information on our states and the transitions. So we have now A, B and the input in, and these we consider in our table. So say we have 0, 0, 0, and then we have and we have now 8 possibilities, 0, 0, 1, 0, 1, 0, 0. These are the 8 possibilities we have, and from this we calculate the values of A prime, B prime and out, and when we have these values we can find the I/O automaton. Okay, let's have a look how A is defined. A is defined, or A prime, how A prime is defined. A prime is not A or in. Okay, so if A is false, then A prime is true, and if in is true, then in the other case then A prime is true. So we have this. Then we have B prime. How is B prime defined? B prime is A XOR in. Okay. Let's check. We have A here, and we have in here, so we have A XOR in. This means we have a 0 here, a 1 here, a 0 here, a 1 here, and here we have 1, 0, 1, 0, and for out we have here B XOR in. Yeah. And yeah, so we have 0, 1, 1, 0, 0, 1, 1, 0. Okay, and now we have to represent the states. We have state 0, 0, then, yeah, let's see where we can go. From state 0, 0, with a 0, we go to state 1, 0. We read, if we read a 0, and we also write then a 0. If we are in state 0, 0, and we read a 1, we go to state 1, 1, and write a 1. If we are in state, let's proceed with state 1, 1. If we are in state 1, 1 and read a 0, then we go to state 0, 1 and write a 1. And if we are in state 1, 1, read a 1, then we go to state 1, 0 and write a 0. Okay, then let's proceed with state 1, 0. If we read a 0 in this state, we go to state 0, 1. And we also write a 0. And if we read a 1, we stay in this state and write a 1. Okay, and if we are in 0, 1 and read a 0, we go to 1, 0, write a 1. And if we read a 1, we go to 1, 1 and write a 0. Yeah, initial state is not defined, so we can choose an arbitrary one, and that's basically it. An I/O automaton maps a word over the input alphabet to a word over the output alphabet. And in order to capture this behavior formally, we introduce the following definitions of the extended transition function and the extended output function. The extended transition function takes, in contrast to the original transition function, not only one symbol of the input alphabet as the second argument, but it takes a word. And we respectively extend the definition in the following. For the extended transition function, I use this calligraphic T here instead of the normal letter T as in the previous definition of the I/O automaton, in order to distinguish these two functions. In the literature and in the old slides, you sometimes find also definitions which use the same symbol for both, for the original transition function and the extended one. But yeah, I have the calligraphic one for better distinguishing it. Okay, and how is this extended transition function defined? we have a recursive definition. In the base case, we are considering words of length 0, so we have the empty word here as the second argument. And if I'm in the state S and the input is the empty word, then the result is the same state as again. More interesting is the other case where the input word is not empty, but where I have at least one letter. And now we give a definition of T, where the first argument is again a state, and the second argument is a word with at least one symbol from the input alphabet. Say it's A, and the remaining word omega is a word also built from symbols of the input alphabet. And if we have such an S and an A omega, then the result of T is S double prime, if and only if there is a state S prime, such that S prime is reachable from S in one step when reading an A. So here I use the original transition function. And so if I can do this one step, then I say that S double prime is simply the extended transition function applied on S prime and omega. And so we have done one step from S with an A to S prime, and respectively the second argument is also smaller, so we have just the omega and not the A included anymore. And by this I can define how I come from a state S when reading a word to a state S double prime. And in a similar way I can define the extended output function, or again I use a calligraphic letter here, this O, and this extended output function takes a state and a word over the input alphabet and maps it to a word of the output alphabet. The output of a state S and the empty word is the empty word. So if I read the empty word, then I also write the empty word. And if I have a word of a length at least one, starting in a state S, then assume that when I'm in state S and I read A, the original output function produces the letter B. Then in the extended output function, I get a word which starts with the letter B, and assuming that when I'm in S and read A, I go to S prime, then the output that is produced starting from S prime with respect to the word omega, which was the remaining word here, gives us omega prime. Then this is the remaining output string. So to say it again, the first letter is simply mapped by the original, is simply obtained by the original output function, and then we have to reuse the extended output function to map the remaining part of the word omega to a word omega prime over the output alphabet. Okay, and if I have now this extended transition function and this extended output function, the behavior B of an I/O automaton is a function that maps a word over the input alphabet to a word over the output alphabet as follows. So the behavior B omega is simply the extended output function from the initial state and with the word omega. So we define as the behavior simply the output we obtain starting from an initial state with respect to the given input. word. Okay, so let's have a look at an example. Assume we want to solve the following problem. Given a word that contains just the letter A, an arbitrary amount of times, we want to figure out if the number of A's in this word is even or odd. And this we want to solve with an I/O automaton. And this could be done by saying, okay, if the number of A's in a word is even, then the I/O automaton should output a word that ends with an E. If the number of A's is odd in a word, then the I/O automaton should output a word that ends with an O. So let's specify this I/O automaton. We have two states, S0 and S1. The input alphabet is A, and the output alphabet contains the two letters E and O. Initial state is S0. I have marked this here in the graphical representation, which also specifies T, the transition function, and O, the output function. For the transition function, we go from S0 to S1 when reading an A, and we go from S1 to S0 also when reading an A. There is nothing much else we can do for the transition function. For the output function, when we go from S0 to S1, the output is an O, and if we go from S1 to S0 when reading an A, the output is an E. And this already gives us the desired behavior, because whenever we read an odd number of A, then the last letter of the outputted word is an O. If we read an even number of A's, then the word that is then the output word ends with an E. So we get the following behavior, or the following extended transition function first. If we are in state S0 and read a word that has an even number of A, then we end up in S0 again. For example, if we have two A's, then from S0 we go to S1, and from S1 we go to S0, and so on. If we have four A's, then we have S0, S1, S1, S0, S1, and S0 again. If we are in S0 and read an odd number of A's, then we end up in S1. And if we are in S1, read an even number of A's, then we end up in S1 again. And if we are in S1, read an odd number of A, then we end up in S0. And what does this mean for the behavior? We said the behavior is simply the output starting in the initial state. So if we read a word that has an even number of A's, then we produce a string that contains the letters O, or the sequence O, E, n times. If we have 2 times n A's, and if we have 2 times n A's, this is certainly an even number, because any number multiplied by 2 is even, and therefore the automaton behaves as expected. The output word ends with an E. And if we have an odd number of A's, so we have 2 times n plus 1 A's, this is certainly an odd number, then we have an additional O in addition to the n OA pairs, and therefore we also have the desired behavior that the output string ends with an O if the input word contains an odd number of A's. To conclude this lecture, I would like to show you how I/O automata and finite automata relate to each other. In particular, I would like to show you how to translate the one into the other and vice versa. And I will start with the translation of I/O automata into finite automata. Such translations can be very useful if you have a tool that can only process one kind of automata. So for example, you have a tool for finite automata and for some reason you have an I/O automaton, then you can easily translate this I/O automaton into the finite automaton and apply your tool on the translation. Okay, so how does this work for translating an I/O automaton into a finite automaton? Assume we are given an I/O automaton A that consists of the following components. We have a set of states S, one initial state I, input alphabet sigma, transition function T, output alphabet theta, and output function O. And from this we want to generate or obtain a finite automaton A prime that reflects the behavior of A in its language. We will see soon what this means, but let's first write down the translation. So the set of states we have in A prime is simply the set of states we have in A, and the only initial state of A prime is the initial state of A, and since A does not have any final states and there is no notion of acceptance in I/O for I/O automaton, the final states are simply all states. Okay, so this was the simple part, and for the more involved part we have to come up with a way to handle or to include the output alphabet of the I/O automaton and the output function. And what we do is we encode this into the alphabet of A prime, and the alphabet is now the cross product of sigma and theta. So we have pairs of input symbols and output symbols as the alphabet of A prime. And respectively we define the transition relation T prime of A prime, and we say we can do a step from state S to a state S prime with symbol AB. Yeah, recall we have here now this pair. We can do such a step if and only if, and now the transition function and the output function come into play. So we can do a step from state S when reading A to a state S prime. Yeah, so from S with A we go to S prime, and the output when doing this step, so when we are in state S, read an A, then we have the output B. This is what we have here. Yeah, and this is already it. So this gives us the transition relation for our finite automaton A prime. And now, how does the behavior of the I/O automaton and the finite automaton relate? Yeah, if we have an input word A1 to AN that is read by the I/O automaton and it produces a word B1 to Bn, then there is a word in the language of A prime that has the following form. So the first symbol is A1 B1, the second symbol is A2 B2, and so on, and the last symbol is AN BN. And this also works in the other direction. So if we have such a word in the language of A prime, then we have the respective behavior for the I/O automaton. Yeah, so we have the two components reflecting the input and the output. Here I have a simple example, and in particular, if we have given an I/O automaton, the translation is really straightforward. It's just a change in notation. So the states become all final states. So we have the double circles here, and the slash, which separates the input and the output, becomes a comma, and we put parentheses for the pairs around it. But that's basically the translation. Yeah? So there is not much more to do if we're given an I/O automaton and want to represent it as a finite automaton. And yeah, again, the trick is that we encode the output in terms of elements of the alphabet of the finite automaton, and we have it then as the labels of the transitions. Now I want to show you the other direction and show you how to obtain an I/O automaton from a finite automaton that shows a corresponding behavior with respect to the language accepted by the finite automaton. And this works as follows. So assume we are given a finite automaton as usual, and what we have to be careful about is that this automaton is not necessarily deterministic, and in order to ensure that we have an automaton that is deterministic and accepts the same language, we simply use the power automaton. So we start from the power automaton and extend it a bit to obtain an I/O automaton. So for the automaton A, we take the power set as the set of states. The initial state is simply the set of all initial states from A. Yeah, so this is one set of PS. Then the alphabet remains the same, the input alphabet. So this is simply sigma. The output alphabet consists of 0 and 1. With this, we represent the final states, as we will see in a second. And the transition function is simply the transition function of PA. Yeah, so this transition relation of the power automaton, we said, is also which is deterministic and complete, is therefore also a function. So we can use this here. And the only thing where we have to do something more is the output function. And we define the output function as follows. If we have a state S prime and a symbol A, then O gives us a 1 if and only if S prime contains a final state. Yeah? And this means if we have an finite automaton, we do the power automaton, and then we take this power automaton and relabel the edges, and we put /0 on all edges which are outgoing from non-final states, and we put /1 on all edges which are outgoing from final states. Yeah, and we will see in a second an example. But how does the behavior of an I/O automaton and the language of an finite automaton relate? You say that omega is a word that is accepted by A, so it's a word that's in the language of A. Then if B, so if the I/O automaton reads this word plus an additional symbol, it produces a word that ends with a 1, and the other output is irrelevant. We just have a 1 at the end of the word, indicating that the input word omega is in the language of A, and if it's not in the language of A, then the last symbol is simply a 0. And to illustrate how this works, let's look at an example, and I switch to my writing space. Given is this automaton here on the left, let's call it A, and on the right hand side I already prepared the power automaton of A, and I want to transform this power automaton into an I/O automaton. So we want to have the I/O automaton of A. And this is very simple. We add /0 to all labels of edges that do not come from a final state. So these are the most edges. We simply add /0 here. And we have only one final state. This is S2, S4. And here we have to be a bit careful, because here we add /1 for both, for A and B. Yeah, and then we remove the double circle here, because an IO automaton does not have any final state. And that's already the translation into an IO automaton. So let's have a look what this means for a word that is accepted by A. So for example, ABA is in the language of A. And if we want to check if ABA is in the language of A, by taking a look at the IO automaton, we have to check the output for ABA plus an additional symbol. I just write a star here because it doesn't matter which symbol we're considering. It can be just an A or a B, doesn't matter. Okay, and if we now have a look, what is the output for ABA and the additional symbol, we get 0, 0, 0, and then it doesn't matter if we take A or B, we get a 1. And this one at the end of the string indicates that ABA is indeed accepted by A, so it's in the language of A. Now one could ask, why do we label the outgoing edges of the final states with a 1 and not the incoming edges? Let's consider the following example. Let's say we have an automaton B, and it consists of one state, which is a final state, and it has one edge labeled with an A that goes to the state again. And now what is the language of B? Now, the language of B is the empty word A, and so on. So it consists of all the words that can be built from letters A, including the empty word. Okay, and if we now apply our construction, then we can immediately take this automaton, because it is when assuming that sigma is A, then it's deterministic and complete. And since this was a final state, we put a 1 here. Okay, and what is the effect of having the 1 here? When we want to check, is epsilon in the language of B? Yeah, if we want to check if epsilon is in the language of B, we have to check if B and some symbol produces a 1, and this is indeed the case. Yeah, so we read 1A, and this string, the produced string, ends with an A, and therefore we can conclude that the empty word epsilon is in the language of B. If we wouldn't put the 1 on the outgoing transitions, we couldn't capture this situation, because we cannot label the incoming edges of initial states with something, and therefore it would not otherwise be possible to capture the empty word. Okay, so with this I would like to conclude this lecture and finish this short introduction on finite automata, where we discussed acceptors that can be used to decide if a word is in a language or not, and transducers, which can also produce output words. And yeah, as an outlook, I would like to point out that finite automata play a very important role in one way or another during the whole course, because they are a very fundamental concept and will be used in other formal modeling languages. And yeah, so we will see them again and again. Okay, thank you very much for watching.